In the early years of World War II, confidence inside the German aviation establishment ran high. Engineers, officers, and pilots of the Luftwaffe believed they possessed not only superior tactics, but superior machines. Their aircraft were sleek, purpose-built, and engineered with precision. In contrast, American planes were often dismissed as oversized, inefficient, and lacking refinement. To many in Germany, the United States was an industrial giant, yes, but one that relied on quantity over quality. Mass production, they believed, came at the cost of true engineering excellence. This belief wasn't born out of arrogance alone. Early encounters in the war seemed to reinforce it. German fighters like the Messerschmitt Bf 109 and Focke-Wulf 190 had proven themselves deadly against a range of opponents. European aircraft design had matured through years of intense competition and rapid innovation, while the United States had only recently begun mobilizing for a global conflict. From the German perspective, American aviation was still catching up. But by 1943, something began to change. Reports started filtering in from Luftwaffe pilots operating over Western Europe. They spoke of a new American fighter, large, heavy, and unlike anything they had seen before. At first glance, it didn't seem particularly threatening. It was bulky, almost awkward in appearance, and far bigger than the nimble German interceptors. Some pilots even joked about it, assuming it would be easy prey. They were wrong. The aircraft was the P-47 Thunderbolt. At high altitude, where many air battles were fought, the P-47 revealed a completely different personality. It could dive faster than almost anything in the sky, using its weight not as a weakness, but as an advantage. German pilots who attempted to pursue it in a dive often found themselves unable to keep up, or worse, risking structural failure if they tried. And when it came to durability, the Thunderbolt was something entirely new. Pilots reported seeing P-47s return to base riddled with bullet holes, engines damaged, control surfaces barely holding together, yet still flying. Stories spread of American fighters absorbing punishment that would have destroyed other aircraft outright. To Luftwaffe veterans, this was deeply unsettling. German aircraft had been designed with performance and efficiency in mind, often sacrificing armor and redundancy. The idea of a fighter built to take hits and keep flying challenged everything they thought they knew about aerial warfare. Then there was its firepower. The P-47 carried 8.50 caliber machine guns, delivering a devastating volume of fire. In a head-on engagement or a brief firing window, it could shred enemy aircraft in seconds. German pilots began to realize that even a short mistake, just a moment in its sights, could be fatal. At first, these reports were met with skepticism. Intelligence officers questioned whether pilots were exaggerating. Engineers assumed there must be trade-offs. No aircraft could be that powerful, that durable, and still be effective in combat. It didn't fit their understanding of design logic. Every strength was supposed to come with a corresponding weakness. But the reports kept coming. Encounters with the P-47 increased as American air operations intensified. Bomber formations escorted by these fighters became harder to intercept. The Thunderbolt wasn't just protecting bombers, it was actively engaging German fighters, disrupting their attacks, and sometimes turning the tables entirely. Its presence forced Luftwaffe pilots to rethink their tactics, often putting them on the defensive. What disturbed German analysts most was not just the aircraft's performance, but what it represented. The United States was not simply producing large numbers of mediocre machines. It was producing aircraft that combined power, resilience, and practicality in ways that didn't align with traditional European design philosophies. The assumption that American engineering lagged behind was beginning to crack. Inside technical circles, quiet debates began to emerge. How had the Americans achieved this balance? How could such a large aircraft perform so effectively at high altitude? And perhaps most troubling of all, what else were they capable of producing?
The myth of American inferiority had been comfortable. It allowed German planners to believe they held a lasting advantage, that their technology and expertise would continue to dominate the skies. But now, that belief was being challenged by real combat experience, by pilots who had faced this new machine and survived, barely. Some began to suspect that the Thunderbolt was not an anomaly, but a sign of something larger, a shift in the nature of industrial warfare. The United States had vast resources, immense manufacturing capacity, and a different approach to engineering, one that prioritized reliability, standardization, and scalability alongside performance. If the P-47 was the result of that system, then Germany might be facing not just a new aircraft, but an entirely new kind of opponent. By late 1943, the tone had changed. The dismissive attitude towards American aircraft was fading, replaced with cautious respect and growing concern. The Luftwaffe was no longer asking whether the P-47 was a threat, it was asking how such an aircraft was even possible. And soon, they would get their answer. Because examining it from a distance was one thing, taking it apart, piece by piece, would be something entirely else.
By late 1943, curiosity inside the German Aviation Command had turned into urgency. Reports from the front were no longer dismissed. They were studied, compared, and taken seriously. The strange, heavy American fighter that pilots had once mocked was now a subject of intense interest. There was only one way to truly understand it. They needed one intact. When a relatively undamaged P-47 Thunderbolt fell into German hands, it was quickly transferred under tight security to the Rechlin Experimental Center, the Luftwaffe's most advanced aviation testing facility. This was where Germany's best engineers and test pilots evaluated captured enemy technology. If there were secrets to uncover, this was where it would happen. From the moment the aircraft arrived, it drew attention. At first glance, it seemed almost excessive. The fuselage was massive compared to German fighters. The wings were thick. The overall structure looked more like a flying tank than a sleek interceptor. Some engineers reportedly approached it with the same assumptions they had always held, that beneath the bulk they would find crude solutions and inefficient design choices. But as they began their inspection, those assumptions started to fall apart. Panels were removed, systems were exposed, and what they found was not crude, it was deliberate. The internal layout of the aircraft revealed a level of organization that was both practical and highly refined. Components were accessible, systems were arranged in a way that made maintenance faster and more efficient. This was not an aircraft designed only for performance in ideal conditions. It was designed to operate reliably in the chaos of war, under constant stress, with minimal downtime. That realization alone was unsettling. German aircraft design had long emphasized precision engineering, often resulting in complex systems that required skilled technicians and careful handling. The American approach, as seen in the P-47, was different. It embraced robustness. It accepted that things would go wrong in combat and built the aircraft to survive those failures. Armor plating around the cockpit and critical systems caught the engineers' attention. This was not standard in many German fighters, where weight savings were prioritized. Yet here was an aircraft that willingly carried extra mass to protect the pilot and vital components. It wasn't just about winning a dogfight, it was about making sure the pilot could come back and fight again. Then there were the redundancies. Control systems, fuel lines, and key mechanical elements showed signs of thoughtful duplication. If one part failed, another could take over. This kind of design thinking required not just engineering skill, but a different philosophy, one that valued long-term operational effectiveness over short-term performance gains. As the examination continued, skepticism gave way to something closer to respect.
Nothing about the aircraft felt accidental. Every design choice seemed to reflect a clear understanding of combat realities. Even details that initially appeared inefficient often revealed their purpose upon closer inspection. The more the engineers studied the aircraft, the harder it became to dismiss it. And yet, the biggest shock was still to come. When they turned their attention to the engine installation, the scale of what they were dealing with became undeniable. The aircraft wasn't just large for the sake of durability. It was built around a power plant that demanded space, cooling, and structural strength. This was not a compromise. It was a commitment to raw power. Before even fully analyzing the engine itself, they could already see the consequences of that choice throughout the aircraft's design. Reinforced mounts, carefully routed systems, and structural elements all pointed to an integrated approach, one where the entire aircraft was built to support and maximize the performance of its core. Test pilots at Rechlin were eager to take the aircraft into the air. When they did, their impressions added another layer to the growing picture. The P-47 handled differently than German fighters. It wasn't as nimble in tight turns, but it was stable, predictable, and incredibly fast in a dive. At high altitude, it performed far better than its size would suggest. It was not trying to be a traditional dogfighter. It was something else entirely, a high-altitude escort, a heavy hitter, a machine designed to dominate in specific conditions and survive encounters that would destroy lighter aircraft. This specialization, combined with its durability, made it far more dangerous than it initially appeared. Back in the hangars, engineers continued their work, documenting everything. Measurements were made, materials were analyzed, manufacturing techniques were studied, and slowly a realization began to take shape. This aircraft was not the product of rushed or inferior engineering. It was the result of a system, an industrial and design philosophy that approached problems differently. Where German engineers sought elegance and efficiency, the Americans had embraced practicality, strength, and scalability. And somehow they had done so without sacrificing effectiveness. For some, this was deeply frustrating. They searched for flaws, for weaknesses that could explain the aircraft's success in simpler terms. Surely there had to be trade-offs, compromises that could be exploited. But the more they looked, the more elusive those answers became. Instead, they found a machine that made sense, not in the way they expected, but in a way that was hard to argue against. By the end of the evaluation, one thing was clear. The reports from the front had not been exaggerated. If anything, they had understated the reality. The P-47 was not just a capable fighter. It was a reflection of a broader shift in how war machines were being designed and built. And at the center of that shift was something the German engineers had yet to fully confront: the true heart of the aircraft, the engine that made it all possible.
By the time German engineers at the Rechlin Experimental Center turned their full attention to the heart of the P-47 Thunderbolt, expectations were already high. They had seen the aircraft's structure, its systems, its philosophy. But engines were different. This was where German engineering had always excelled. Precision, efficiency, performance. This was their domain. At first glance, the power plant seemed almost excessive. The Pratt & Whitney R2800 double Wasp was enormous. An 18-cylinder twin-row radial engine, it dominated the front of the aircraft. Compared to many German inline engines, it looked bulky, even primitive in layout. Radial engines, after all, were often considered less aerodynamically efficient. The Germans had long favored liquid-cooled inline designs for their sleek profiles and high-speed potential. But as the engineers began their analysis, that initial confidence began to erode. The first shock came from the sheer output, over 2,000 horsepower, reliably delivered, not in ideal test conditions, but in operational reality.
This wasn't just peak performance, it was sustained power, available at high altitudes where many engines struggled to maintain efficiency. How? That question drove the investigation deeper. The answer lay not in a single breakthrough, but in a combination of systems working together with remarkable precision. The turbo-supercharger setup, in particular, drew intense attention. Unlike simpler supercharging methods, this system used exhaust gases to drive a turbine, compressing incoming air and maintaining engine performance even in thin, high-altitude air. The complexity of it was staggering. Ducting ran through the fuselage, connecting the engine to the turbo system mounted further back. Airflow, heat management, pressure control, every element had to be carefully balanced. And yet, somehow, it worked. Not just in theory, but in combat conditions, under stress, with pilots pushing the aircraft to its limits. German engineers were no strangers to forced induction systems, but this implementation was on another level. It wasn't just about boosting power, it was about doing so reliably, repeatedly, and across a wide range of operating conditions. And reliability became the next point of focus. As components were examined more closely, a pattern began to emerge. The tolerances were precise, but not excessively so. Materials were chosen not just for performance, but for durability. The engine was designed to keep running even when conditions were far from ideal. Dirt, damage, wear, these were expected, and the design accounted for them. This was not a fragile masterpiece, it was a workhorse. That realization was difficult to ignore. German engines, while powerful and advanced, often required careful maintenance and could be sensitive to damage. They were optimized for performance, but sometimes at the cost of resilience. The R2800, by contrast, seemed almost indifferent to punishment. It was built to endure. Test data reinforced this impression. The engine could take hits and continue operating. It could run for extended periods without catastrophic failure. Even when partially damaged, it often retained enough functionality to bring the aircraft and the pilot back home. In the brutal environment of aerial combat, this wasn't just an advantage, it was a game changer. As the analysis continued, another uncomfortable truth began to surface. It wasn't just about engineering design, it was about production. The more the Germans studied the engine, the more they realized that replicating it would require more than understanding its mechanics. It would demand an industrial system capable of producing such engines consistently, at scale, and with reliable quality. Precision machining, standardized parts, advanced metallurgy, and efficient assembly processes, all working together. And that was where the real gap became clear. Germany, under increasing strain from Allied bombing and resource shortages, simply did not have the same industrial capacity. Even if they could design a comparable engine, producing it in large numbers with consistent performance was another challenge entirely. The R2800 was not just an engine, it was the product of an entire ecosystem. Factories, supply chains, engineering standards, and logistical support all aligned towards a single goal. It represented a level of industrial integration that was difficult to match, especially under wartime conditions. For some engineers at Rechlin, this realization was deeply frustrating. They could see the brilliance of the design, they could understand how it worked, but bridging the gap between understanding and replication, that was something else entirely. There were attempts to identify weaknesses. Heat management, system complexity, the vulnerability of external ducting, these were all noted. In theory, they offered points of failure, but in practice, the overall design mitigated many of these risks. Damage that might cripple another engine system often failed to bring down the Thunderbolt. It was resilient by design, and that resilience extended beyond the engine itself. The entire aircraft had been built around the idea that it would be pushed to its limits and beyond. The engine was simply the most visible expression of that philosophy. By the end of the evaluation, the conclusion was unavoidable. The Pratt & Whitney R2800 double Wasp was not something that could be easily copied. not because it was mysterious or beyond comprehension, but because it represented a different way of thinking about engineering, about production, and about war itself. It forced a shift in perspective. The Americans were not sacrificing quality for quantity. They were achieving both in ways that challenged long-held assumptions. The idea that mass production meant inferiority no longer held. And for the engineers who had once dismissed American aircraft, that realization carried a quiet, unsettling weight. Because if this was what the United States could produce in 1943, what would come next?
By the time German engineers finished dissecting the machine at the Rechlin Experimental Center, a deeper question had begun to take shape. The aircraft made sense. The engine made sense. The systems, the structure, the philosophy, it all fit together with a kind of clarity that was hard to ignore. But who had put it all together? Who had made the decisions that led to this balance of power, durability, and practicality inside the P-47 Thunderbolt? The answer led far beyond Germany, across the Atlantic, to a designer whose story was as unconventional as the aircraft itself, Alexander Kartveli. Kartveli was not American by birth. He came from Georgia, a region that had seen instability, conflict, and political upheaval. Like many engineers of his generation, his path was shaped by displacement and opportunity. Eventually, he found his way to the United States, where a rapidly expanding aviation industry offered something rare: the freedom to experiment, to build, and to think differently. And think differently he did. From the beginning, Kartveli approached aircraft design with a mindset that contrasted sharply with traditional European philosophies. He was less interested in creating the lightest or most elegant machine, and more focused on building something that could survive the brutal realities of combat. He understood that in war, performance alone was not enough. Aircraft were pushed beyond their limits, pilots made mistakes, and damage was inevitable. So instead of designing for perfection, he designed for reality. The P-47 was the result of that thinking. It was never meant to be the most agile fighter in the sky. It was not designed to win tight turning dogfights against lighter aircraft. Instead, it was built around a different set of priorities: high-altitude performance, overwhelming firepower, and above all, survivability. Kartveli made a critical decision early in the design process. He would build the aircraft around a powerful engine, not just accommodate it, build around it. The Pratt & Whitney R2800 double Wasp would be the core, and everything else would support its performance. That decision defined the aircraft. The large fuselage, the reinforced structure, the space required for turbo-supercharging systems, all of it traced back to that choice. Where others might have tried to minimize size and drag, Kartveli accepted the trade-offs. He understood that raw power, properly managed, could overcome many disadvantages. And he paired that power with protection. Armor plating was not an afterthought, it was a requirement. The pilot sat inside a heavily protected cockpit, shielded from gunfire that would have been fatal in many other fighters. Fuel tanks were designed to reduce the risk of fire. Critical systems were positioned and reinforced with survival in mind. This was not just engineering, it was strategy. Kartveli wasn't designing for ideal conditions, he was designing for chaos. He assumed that the aircraft would be hit. He assumed that systems would fail, and he built in ways to keep the aircraft flying anyway. At first, not everyone agreed with his approach. Early in its development, the P-47 faced skepticism even within the United States. Some questioned its size, its weight, its lack of agility. Compared to sleeker fighters, it seemed almost excessive. There were doubts about whether such a large aircraft could compete in the fast-paced, unforgiving environment of aerial combat. But Kartveli held his ground. He believed that the future of air combat was changing, that altitude, speed, and firepower would matter more than tight maneuvering alone.
And most importantly, he believed that keeping pilots alive, giving them a machine that could bring them home, was just as important as winning engagements. And as the war progressed, those ideas were put to the test, and they worked. The P-47 proved itself not by dominating in every category, but by excelling where it mattered most. It could dive faster than its opponents, escape when necessary, and deliver devastating firepower when the opportunity arose. It could absorb damage and continue fighting, or disengage and survive. Pilots began to trust it. That trust became one of its greatest strengths. Knowing that their aircraft could take hits and still fly changed how pilots approached combat. They could be more aggressive, more confident, more willing to engage. And in war, that psychological edge could be just as important as technical performance. Back at Rechlin, German engineers were beginning to understand that what they had examined was not just a machine, it was the product of a philosophy. A philosophy shaped by a designer who had seen instability, who understood uncertainty, and built accordingly. The P-47 was not elegant in the traditional sense. It was not minimal. It did not chase perfection in the way German engineers often did. Instead, it embraced complexity where necessary, strength where possible, and compromise where it made sense. And in doing so, it achieved something unexpected. It worked. Not just in controlled conditions, not just on paper, but in the unpredictable, violent reality of war. For those who had once dismissed American aircraft as inferior, this realization was becoming harder to ignore. The Thunderbolt was not an accident. It was not a fluke of engineering. It was the result of deliberate choices, guided by a different understanding of what an aircraft needed to be. And as its impact in the skies over Europe continued to grow, one thing became increasingly clear. This way of thinking was changing the war.
By 1944, the skies over Europe had become a proving ground, not just for pilots, but for entire philosophies of war. What had begun as skepticism toward the P-47 Thunderbolt had now evolved into something far more serious. The aircraft was no longer an unknown, no longer underestimated. It was a constant presence. American bomber formations pushed deeper into German-controlled territory, and with them came the Thunderbolts. High above the continent, where the air was thin and unforgiving, these aircraft operated with a kind of confidence that had once seemed impossible. They weren't just escorts anymore. They were enforcers. Luftwaffe pilots began to feel it. Interceptions that had once been routine were now far more dangerous. Approaching a bomber formation meant dealing not only with defensive gunfire, but with fast, heavily armed fighters that could strike hard and disengage just as quickly. The P-47 didn't need to outturn its opponents. It chose when to fight, and more importantly, when not to. That control changed everything. German pilots quickly learned that chasing a diving Thunderbolt was a mistake. Its weight and power allowed it to accelerate rapidly, reaching speeds that pushed the limits of what other aircraft could safely handle. Many who tried to follow either lost control or were forced to break off. What had once looked like a weakness, its size, had become one of its greatest strengths. And then there was its role on the ground. As Allied forces advanced across Europe, the mission of the P-47 expanded. It became one of the most effective ground attack aircraft of the war. Armed with bombs, rockets, and its 8.50 caliber machine guns, it could tear through convoys, armored vehicles, supply lines, and troop concentrations. For German forces on the ground, the sound of a diving Thunderbolt became something to fear. It could appear suddenly, strike with overwhelming force, and disappear before an effective response could be mounted. Its durability meant it could survive ground fire that would bring down other aircraft. Even when hit, it often made it back. Again and again, it returned. This persistence had consequences. Supply routes became more dangerous. Reinforcements moved more slowly.
Morale began to erode, not just in the air, but on the ground. The Thunderbolt wasn't just fighting aircraft anymore, it was shaping the battlefield itself. Back in Germany, analysts and engineers watched these developments with growing concern. The evaluations conducted at the Rechlin Experimental Center had already revealed the aircraft's strengths. Now, those strengths were being demonstrated daily on a scale that could not be ignored. It wasn't just about one aircraft, it was about what that aircraft represented. The United States had managed to combine engineering, production, and operational strategy into a unified system. The P-47 was one piece of that system, but it was a powerful one. It showed what could happen when industrial capacity and design philosophy aligned toward a clear purpose. And there were more coming. That realization may have been the most unsettling of all. The Thunderbolt was not a rare or experimental machine. It was being produced in large numbers, deployed across multiple fronts, and continuously improved. Losses were replaced, squadrons remained operational, pressure never let up. For the Luftwaffe, this created a growing imbalance. Even as German pilots fought with skill and determination, they were increasingly outmatched, not always in individual engagements, but in the broader picture. They faced an enemy that could absorb losses, adapt quickly, and maintain constant pressure. The margin for error became smaller with each passing month, and the Thunderbolt played its part in that shift. Its combat record reflected this reality. It was not invincible, but it was effective. Its combination of firepower, speed, and durability gave it an edge in many situations. Pilots who flew it understood its strengths and used them well. Diving attacks, high-speed passes, coordinated strikes. It wasn't about elegance, it was about results. Over time, respect replaced doubt. German pilots no longer underestimated the aircraft. Engineers no longer dismissed its design. The lessons learned from examining it, from fighting against it, became part of a broader understanding, one that came too late to fully counter. Because by then, the balance had already begun to shift. The Thunderbolt had helped secure air superiority in key regions. It had protected bombers, disrupted defenses, and supported ground forces. It had proven that a different approach to design, one that prioritized survivability, power, and practicality, could succeed on a massive scale. And behind it all was a simple, undeniable truth. The assumptions were wrong. American aircraft were not inferior. Their engineering was not crude. Their approach was not flawed. It was simply different, and in many ways better suited to the kind of war that was being fought. The myth that once gave confidence had been replaced by reality. A reality forged in combat, confirmed in analysis, and impossible to ignore. In the end, the story of the P-47 Thunderbolt was not just about a single aircraft. It was about a turning point, a moment when perception collided with truth, and the outcome of that collision reshaped the skies over Europe. And once that shift began, there was no turning back.